All right, everyone. In this video, I'm going to be running through the Honors Chemistry Unit 7 study guide. All right, so first, we have aluminum added to a solution of iron 4 sulfate. So let's see. So aluminum is going to be Al. That's going to be solid. Added to a solution of iron 4 sulfate. So Fe SO42, and because it's a solution that's going to be aqueous. All right, so there's going to be a single replacement reaction, SRR, single replacement reaction. So the aluminum is going to try to replace the iron. We need to check our activity series to see, can aluminum replace iron? Yes, it can, because aluminum's higher, so this will proceed. All right, the aluminum will now bond with the sulfate, giving us aluminum sulfate, which is going to be Al2SO43. Because this occurs in solution, that's going to remain aqueous in solution. The iron gets bumped out, so plus Fe solid. And now we balance this out. I like to grab this term first because it has the most ions. So let's see, 3 sulfates here and 2 sulfates here. So I need to put a 3 there and a 2 here. It gives me 4 aluminums. And for irons, looks like 3. So 4, 3, 2, 3. Single replacement reaction. Okay. Number 2, solutions of strontium bromide and aluminum nitrate are mixed. So before we even work this one out, let's see what the products are going to be and whether this will actually go through. So strontium nitrate is going to be one product. If I check my list here, the solubility table, strontium nitrate. In fact, I know all nitrates are going to be aqueous. The other product is going to be aluminum bromide. That is aqueous as well. So because my 2 products are going to be aqueous, this is going to be no reaction, because I'm going to start with 2 aqueous compounds, meaning 4 ions randomly floating in water. I'm going to end with 2 aqueous products, which means the same 4 ions randomly floating around in water. So no reaction occurs. This would be a double replacement, but it's not. It's no reaction. All right, liquid decane combusts. So clearly it's a combustion reaction. So in a combustion reaction, our fuel, which in this case is C10H22 liquid, is going to react with oxygen gas, so that's O2, yielding carbon dioxide and water. The CO2 is going to be a gas. The liquid, you can really go either, the water, either liquid or gas. I tend to go liquid as its natural state there. All right, my recommendation for this is H, then C, then O. So starting with the H's, I have 22 and 2, so I'm thinking 11. But before I put 11, I'm going to ask myself, is that okay? Or is that going to cause a problem? And I know it's going to cause a problem because that'll give me an odd number of O's, which I can't have. Notice on the left, I have 2 here. So I'm going to double this. I say, when in doubt, double it. So I'm going to go 2. Now that gives me 44 H's. So now I'm going to put 22 here. H's are good. Carbons, 2 times 10 is 20. So I'm going to put a 20 here. We now just need our oxygens. A little trick, it's going to be this number plus half of this number, so 31. But just working it out the long way, 20 times 2 is 40. That's 40 oxygens. 22 times 1 is 22. 40 and 22 is 62 oxygens needed, so 31. All right. Iron 3 carbonate breaks down over time. So that's going to be Fe2 parentheses CO3 3. Now, this is an ionic compound. I don't hint at the state, but you should know that ionic compounds are always going to be solid unless you're told otherwise, like if they're solution, that'll be aqueous. So this one is going to be solid. Breaks down over time. So the type of reaction here is going to be a double replace. Oh, no, decomposition reaction. Okay. So this is going to be one of those special ones that you are asked to memorize. So with this one, metal carbonates are going to decompose into metal oxides plus carbon dioxide gas. So iron 3 carbonate is going to form iron 3 oxide. That's going to be Fe2O3. That'll also be solid because it's ionic. And CO2 gas. And now we just need to balance this. All right, well, I would love to keep my carbonates together, but I can't. So I got to go letter by letter. This might be a little bit of a challenge. All right. 2 irons, looks like 9 oxygens and 3 carbons. Let's just try a 3. Ooh, this looks easy. Let me try 3 here for the CO2. That gives me the 3 carbons I need. That gives me 6 oxygens here plus 3 is 9. Wow, that was way easier than I thought it'd be. So 1, 1, 3 decomposition reaction. Number 5, cobalt burns in air, so it forms a 3+ charge. So we have cobalt is CO, that's going to be a solid because it's a metal. Burns in air means plus O2 gas. What type of reaction? Synthesis, not combustion. Just because something burns doesn't mean it's combustion. In order to be combustion, the thing burning has to be one of those carbon hydrogen-based fuels. So this is going to be synthesis. They're going to come together to form cobalt oxide, some form of that. Now, you're not just going to blindly smush these together and say COO2. We're going to see what it's going to form. Now, assume it forms a 3+ charge, so we're going to end up with cobalt 3 oxide, which is going to be CO2O3. And because that's ionic, we should assume that that's a solid. Now we balance. Let's see, I'm seeing 3 O's and 2 O's. When I see 3's and 2's, I think 2's and 3's. So we're going to put a 3 there and a 2 there, and then a 4 here, and we're good. Come on. Number 6. All right, solutions of. Whenever I see that, it's probably going to be a double replacement, right? So manganese 2 acetate, strontium sulfide. Again, let's check to see whether something will actually form here before we waste our time writing out a balanced equation. So the first product is going to be manganese 2 sulfide. If I check my list, manganese 2 sulfide is solid. So I am going to form a precipitate, so I know this will happen. My other product is going to be strontium acetate. I know that all acetates are aqueous, so this will occur because we're going to have a solid and an aqueous product. All right, and we are going to sketch this one as well. So manganese 2 acetate is going to be MnC2H3O2, and since it's solutions of aqueous, that's going to react with strontium sulfide, SRS, aqueous, and manganese 2 sulfide is one product, so that's going to be MnS. I already looked that up, and that's solid. And lastly, strontium acetate, SrC2H3O2, and that is aqueous. And lo and behold, already balanced. Sometimes works out nicely like that. All right, let's do a sketch. So your teacher might do sketches a little different, so go by what your teacher goes with. For me, I like to do beaker number 1 plus beaker number 2 yields beaker number 3 for double replacements. Because remember, these are water-based reactions. We're not, I'm not taking solid manganese 2 acetate and throwing it at solid strontium sulfide. In fact, if you did that, you would actually not get a reaction. If you just chuck the 2 solids together and mix them, nothing's going to happen. They really need to be aqueous in order for those ions to really switch. So what I really have here is manganese ions with a 2+ charge and acetate ions with a 1- charge floating around. Now inside this I have water, and I want to show the water's angled in a particular direction, with the negatively charged O's pointing towards the positively charged ion and the positively charged hydrogens pointing towards a negative ion. Think of these as little fish or little tadpoles swimming towards the positive things in their life and away from the negative things in their life. We're going to do a similar thing here. We're going to have strontium 2+ and sulfide 2- with water swimming towards the strontium and away from the sulfide. In our products beaker, we have MnS, which is a solid, so that's going to settle at the bottom as our precipitate. I like to show a line because you'll literally see it layering up. And then we're going to have strontium acetate floating around up here. All right. Here's our water molecules, just a few of these, and we're good with that one. All right, number 7, carbon dioxide gas reacts with liquid water. CO2 gas plus H2O liquid. All right, this is going to be another one of those special ones that you had to memorize. So in here, we are going to form carbonic acid. In fact, this happens naturally. Water is slightly acidic because CO2 will naturally get from the air into the water, and that'll naturally form carbonic acid. So carbonic acid is C2HO3. It's the acid form of carbonate. That's going to be aqueous because all acids need to be aqueous in order to be acids. And I think we're already balanced. Two H's, 1 O, 1 O, 3 O's, 3 O's. Good. Oh, type of reaction again is going to be two reactants forming one product, synthesis. Make sure I didn't forget some types. I think I didn't write double replacement for the last one, but DRR, double replacement reaction, synthesis, good. All right, number 8, potassium hydroxide and sulfuric acid solutions are mixed. So potassium hydroxide, I'm going to recognize that as a base because it ends in hydroxide. And phosphorus acid is obviously an acid there. So this is going to be a base plus an acid. So this is going to be an acid-base neutralization reaction, which if your teacher didn't specifically mention, you can just call this one a double replacement. But if you've learned that it's an acid-base neutralization, we want you to go with that terminology. An acid plus a base is going to yield water plus a type of salt, which is just any ionic compound that's not an acid or a base. All right, potassium hydroxide solution is going to be KOH aqueous. Phosphorus acid is the acid form of phosphite, so H3PO3 aqueous. This really acts like a double replacement, so my K is going to bond with my PO3, giving me K3PO3. And that is going to be aqueous because this is a water-based reaction. My H is going to bond with my OH. So when H and OH bond, we get, I put a second yield arrow. We're going to get H2O. H2O, and that's going to be liquid water. So at this point, we need to balance. You may find it helpful to temporarily call this HOH when you're balancing neutralization reactions, H parentheses OH. This gives me 4 terms now. Potassium hydroxide, what I call front hydrogens, and phosphite. Potassium, phosphite, front hydrogens, hydroxide. It just helps kind of balance it. Otherwise, you got to split up all the O's and all the H's and all that. All right, so with this in mind, let's start with, I often go to the one with the most ions. Here we kind of have a two-way tie. Let's start with this potassium phosphite. All right, 3 Ks, 1 phosphate. So let's start with the Ks. I'm going to put 3 there. That gives me 3 hydroxides. Here I have 1 hydroxide, so let's put a 3 there. That's 3 front hydrogens, and looks like we're good. I'm just going to change this one back to liquid water, H2O. And we have our reaction done. Okay, number 9, potassium chlorate decomposes. So clearly it's going to be a decomposition reaction. And this is going to be another one of our special cases that you need to know. So potassium chlorate is going to be KClO3. That's going to be a solid because it's aqueous. And you should know that chlorates decompose, or metal chlorates decompose into metal chlorides plus oxygen gas. So this is going to form potassium chloride plus O2 gas. Potassium chloride being ionic is going to be a solid. And now we just balance. So it looks like the oxygens don't quite work right now. I'm seeing 3 and 2, so I'm thinking 2 and 3. Let's put a 2 there and a 3 there. And it looks like I just need a 2 there and we're good. All right, number 10, potassium nitride decomposes into its 2 elements over time. So this is obviously going to be decomposition. Potassium nitride is going to be K3N, and that's going to be a solid because it's aqueous. Decomposes into its 2 elements, meaning potassium and nitrogen. Potassium is a metal, so we just write it as K solid. Nitrogen is a Brinkelhoff or a diatomic element, so I'm going to call that N2. That's naturally a gas, so I'm going to put a G there. And now we just balance this one out. Let's put a 2 there for the nitrogens and a 6 there for the potassiums. Did I skip number 10? No. Number 11, barium is added to a lithium phosphate solution. All right, so this one's going to be, looks like a single replacement reaction. Barium is Ba solid, added to a lithium phosphate, Li3PO4 aqueous. All right, so before we write out what's going to happen here, let's check our activity series and see if barium is able to replace lithium. Well, lithium is at the very top of the list, so in fact, nothing can replace lithium. This will yield no reactions. We can even cross out the SRR if we want. No reaction is going to occur. Literally, your barium piece will just sink to the bottom and remain just like that. Nothing will happen because barium is unable to replace the lithium ions in solution. Sulfuric acid decomposes. So this is going to be H2SO4 aqueous, decomposing. All right, so decomp, obviously. This is another one of our reactions that you should have memorized. So sulfuric acid is going to form sulfur trioxide, SO3, which is going to be a gas, plus liquid water, H2O. Okay. And I think this is already balanced. Let's see. Yep, looks like it's already balanced there. Number 13, aluminum is added to nitric acid. So Al solid plus HNO3 aqueous. All right, this is going to be a single replacement reaction. When we say metals replace metals or halogens replace halogens, we can also say metals will sometimes replace hydrogen. And that's what's going to happen here. The aluminum is going to try to replace hydrogen. So we check if aluminum is able to replace hydrogen. It is. So my products are going to be aluminum nitrate, which is AlNO3. Since this occurs in solution, it's going to remain aqueous in solution. What gets bumped? Well, the hydrogen. And since hydrogen's a Brinkelhoff or a diatomic, we're going to write H2 gas. And now we just balance. So let's see. I need 3 nitrates and 3 nitrates. So I can put a 3 there. Now that's 3 hydrogens, and I have 2 hydrogens. So I can already tell that I need to double this. So instead of 3, I'm going to need to put a 6 here. That gives me my 6 hydrogens, and I can put a 3 there for 6 hydrogens. But let's go back and fix nitrate. By putting a 6 there, I now need to put a 2 here and a 2 there. 2, 6, 2, 3. Cobalt 3 oxide reacts with water. So CO3 plus 2 minus CO2O3, that's going to be a solid because it's ionic, reacts with water, which we can assume in its natural state will be a liquid. Okay, here is one of our special types of synthesis reactions that you need to know. You need to know the metal oxide plus water will yield a metal hydroxide. So in this case, it's going to be cobalt 3 hydroxide, which is COOH3. That's going to be a solid because it's ionic. Let's work out the balanced equation here. All right, I'm seeing 4 O's on the left, 3 on the right. Looking at my H's, I'm seeing 3. Let's see. I'm going to need more O's. Let me try just this, a 2 here and a 3 there to balance out my H's. Let's see what that does. Could it really be that easy? 6 H's, 6 H's, 3 O's, 3 O's, 2 cobalts, 2 cobalts. Oh, very nice. All right, and reaction type, this is again going to be synthesis. And last but not least, butanol combusts. So here we have C4H9OH. I guess I didn't tell you the state, but I'll probably edit this in to the document. Let's call that a liquid. So liquid butanol combusts, so plus O2 gas yields CO2 gas plus H2O liquid. All right, now you might be wondering, why is it C4H9OH? Why doesn't that last H go with the others? Well, it sometimes can be written that way, but you usually see it written this way because this is an example of an alcohol. Alcohol is always in an OL, and the alcohol has to have an OH attached to it. It's very important that there's OH kind of stuck on there. So a lot of times you'll see it written like this with the OH written together. All right, the only change that makes is it kind of, you just got to not forget that there's that extra H and that extra O there when you balance. All right, let's start with the H's again. I'm going to treat this as 10 hydrogen. So I'm seeing 10 and 2, which requires a 5. Now, if there weren't an O here, I would say we need to double that. But let's give it a try, because that extra O there enables some odd possibility. All right, carbons, 4. Let's put a 4. Let's count our O's. So I have 4 times 2 is 8. 5 times 1 is 5. I need 13 O's. How can I get 13 O's? Well, I want to leave this one alone, because if I put anything here, it's going to mess all those up. So let's leave 1 here and get 12 more by putting a 6 there. So 1, 6, 4, 5, and we're balanced. Okay, hopefully you made it through this pretty well. Good luck on your upcoming quiz.